Good afternoon, everyone. My name is Neha. I'm from IT department. My topic is transfer learning in CNN. Introduction. Transfer learning leverages pre-trained models to enhance the performance of convolutional neural networks on a specific task. This approach significantly reduces the training time and enhances the accuracy, especially in scenarios where data is limited. But utilizing the existing knowledge encapsulated in pre-trained models, organizations can achieve superior results with increased efficiency. Transfer learning is a powerful technique in deep learning, where a model developed for one task is reused as the starting point for the model on a second related task. In the context of convolutional neural networks, transfer learning allows us to leverage pre-trained models such as VGG, ResNet, or Inceptions that have been trained on large datasets like ImageNet. These pre-trained models have already learned to detect the generic features like edges, textures, and shapes in images, which are useful across various computer vision tasks. Introduction to transfer learning. Definition and importance. Transfer learning involves taking a model trained on one task and adapting it to perform a different but related tasks. This method is crucial in deep learning as it decreases the need of massive datasets and extensive computational resources, making AI more accessible and efficient. Transfer learning in convolutional neural network is highly significant because it enables the development of accurate and efficient models, especially when data or computing power is limited. Training deep CNN from scratch requires large labeled datasets and extensive computational resources, which are not always available. Transfer learning solves this problem by reusing the pre-trained models that have already learned useful features representations from large datasets like ImageNet. This not only speeds up the training process but also improves the performance, particularly when working with the small or domain specific datasets. Furthermore, it reduces the risks of the overfitting and makes it easier for researchers and developers to apply deep learning to new tasks without needing expert knowledge in model design. Historical context. The concept of transfer learning has evolved alongside advancements in machine learning. Initially focused on traditional models, it gained traction with the rise of deep learning, particularly in computer vision, where large datasets like ImageNet enable the creation of powerful pre-trained data models that others can fine-tune for various applications. The concept of transfer learning has its roots in cognitive science and psychology, where humans are known to apply knowledge from previous experiences to new but related situations. In new machine learning, the idea evolved over time but gained significant traction with the rise of deep learning and convolutional neural network. Initially, CNN were trained from scratch for each task, which required massive label datasets and high computational power. However, as deep learning matured, a large-scale datasets like ImageNet, introduced in 2009, enabled researchers to train powerful CNN architectures such as AlexNet 2012, VGGNet, which was introduced in the year of 2014, and ResNet is introduced in the year of 2015. Key applications in CNN. Transfer learning in convolutional neural network has transformed fields such as image classification, object detection, and natural language processing. By applying pre-trained models, organizations can achieve high accuracy with minimal resources. Notable applications include transfer learning for medical image analysis, where limited annotated data is typical, and real-time object detection in self-driving technologies. Transfer learning in CNN is widely used across various domains where image analysis is critical but data availability is limited. One of the most impactful application in medical imaging where pre-trained CNN are fine-tuned to detect the diseases such as cancer, pneumonia, or retinal disorders using relatively small data sets. In facial recognition and biometrics, transfer learning helps in adapting existing models to specific environment or population. It's also essential in object detection and classification tasks such as recognizing the traffic signs or detecting the defects in industrial products. In agriculture, CNN, which with transfer learning are used for plant diseases detection and crop monitoring. Additionally, satellite and remote sensing imagery analysis benefits from transfer learning to detect land cover, water bodies, or urban changes. Techniques and approaches. Fine-tuning strategies. Fine-tuning involves updating the weights of the pre-trained models on a new dataset. This process typically focuses on the last few layers, allowing the model to adopt its learned features. Techniques like layer freezing and selective retraining enhances the efficiency and effectiveness, ensuring that the model retains critical learned knowledge while adapting to a new domain. Fine-tuning is a critical step in transfer learning that involves adjusting a pre-trained CNN model to better fit a new task specific dataset. The most common strategy is to freeze the early layers of the model since they learn general features like edges and textures and only retrain the deeper layers which are more specialized. This approach saves training time and reduces the risk of overfitting. Feature extraction methods. This approach uses a pre-trained models as a fixed feature extraction, where only the convolutional layer are utilized to generate input features for a new classifier. By applying this method, organizations can leverage existing models to effectively reduce computation time and avoid overfitting, especially when labeled data is scarce. Feature extraction in transfer learning involves using a pre-trained CNN as a fixed feature extractor where the convolutional base of the network is retained and only the facial final classifier layer are replaced and trained on the new dataset. This method leverages the CNN's ability to learn hierarchical features from simple edges in early layers to complex patterns in deeper layers. One common approach is to remove the top fully connected layers of a pre-trained model like VGG16, ResNet, or Inception and feed the output of the last convolutional block into a new classifier, such as a softmax layer or support vertex machine. Transfer learning frameworks and libraries. Numerous frameworks and libraries facilitate the implementation of transfer learning with CNN. Popular options includes TensorFlow, Keras, and PyTorch, each providing extensive tools and pre-trained models. These platforms streamline the process, allowing the developers to easily customize and deploy transfer learning solutions across various applications. Key applications in CNN. Transfer learning in convolutional neural network has transformed fields such as image classification, object detection, and natural language processing. By applying pre-trained models, organizations can achieve the high accuracy with minimal resources. Notable applications include transfer learning for medical images analysis, where limited annotated data is typical, and real-time object detection in self-driving technologies. Transfer learning in CNN is widely used across various domains where image analysis is critical but the data availability is limited. One of the most impactful applications in the medical imaging, where pre-trained CNN are fine-tuned to detect the disease such as cancer, pneumonia, or retinal disorders. Conclusion. Transfer learning in CNN provides significant advantages by harnessing pre-trained models for diverse tasks. By implementing the techniques such as fine-tuning and feature extraction, organizations can minimize the data requirements and improve model performance. The adoption of establishment frameworks further enhances the accessibility and efficiency of transfer learning, driving innovations in AI applications across industries. Thank you.